con los terroristas.
And do the Harlem Shake. The Harlem Shake.
Con los terroristas.
The Harlem Shake.
Con los terroristas. Con los terroristas.
The Harlem Shake.
In electronics, a Schmitt Trigger is a circuit with positive feedback and a loop gain greater than 1. The circuit is named a trigger because the output retains its value until the input changes sufficiently to trigger a change. In the non-inverting configuration, when the input is higher than a certain chosen threshold, the output is high. When the input is below a different chosen threshold, the output is low. And when the input is between the two levels, the output retains its value. Most of the following applications use CMOS-Schmitt as characteristic to either simplify design or increase performance. Some of the applications could not be done at all with another logic family. The circuit in this family are assigned to square wave converter. Because of input symmetry, the Schmitt trigger is easily biased to achieve 50% duty cycle. The high input impedance simplifies the selection of the biasing resistor and coupling capacitor. Since CMOS has a wide supply range, the Schmitt trigger could be powered from split supplies. This biases the mean threshold value around 0 and makes direct coupling from an up and up output possible. We see a frequency to voltage converter that accepts many waveforms with no change in output voltage, although the energy in the waveforms are quite different. We see a frequency to voltage converter that accepts many waveforms with no change in output voltage, although the energy in the waveforms are quite different. It is only the frequency that determines the output voltage. Since the output of the CMOS-Schmitt pulls completely to the supply rails, a constant voltage swing across the capacitor C1 causes a current to flow through the capacitor dependent only on frequency. Light-activated switch couldn't be simpler. The input voltage rises as light intensity increases. When BT is reached, the output will go low and remain low until the intensity is reduced significantly. Schmitt triggers are often used to generate fast transitions when slow varying function exceeds a predetermined level. In this figure, we see a typical circuit, a light-activated switch. The high impedance input of the CMOS-Schmitt trigger makes biasing very easy. Most photocells are several kilowatts brightly illuminated and couple megawatts dark. Since CMOS has 10-12 typical input impedance, no effects are felt on the input when the output voltage changes. A CMOS application note wouldn't be complete without a low power application. This figure shows a simple RC oscillator with only 6 Rs and Cs, with only 6 resistors and capacitors, and 1 hex CMOS trigger. 6 low power oscillators can be built. The square wave output is approximately 50% duty cycle because of the balanced input and output characteristics of CMOS.
Here are the advantages of the Schmitt Trigger. The first one is that it has high impedance input, which is typically 1012 watts. Next advantage is that balanced input and output characteristic there, which is the thresholds are typically symmetrical to 1/2 VCC, and output source and sink equals current. Output drive to supply rails. Next advantages is that positive and negative going thresholds show low variation with respect to temperature. Wide supply range, which is 3 volts to 15 volts. Split supply possible. Next advantages is that it has low power consumption even during transitions. High noise immunity is 0.7 VCC typical. Next advantages is that application demonstrating how each of these characteristics can become a design advantage will be given later in the application note. The input of the Schmitt Trigger goes through a standard input protection and is tied to gates of 4 stacked devices. The upper 2 are P-channel and the lower 2 are N-channel. The transistors P3 and N3 are operating in the source follower mode and introduce hysteresis by feeding back the output voltage out to 2 different points in the stack. When the AC on form a voltage divider network biasing the source of N2 at roughly half the supply. When the input is a threshold voltage 1/2 VCC, N2 begins to turn on and regenerative switching is about to take over. Any more voltage on the input causes out to drop. When out drops, the source of N3 follows its gate, which is out. The influence of N3 in voltage divider with N1 rapidly diminishes, bringing out down further yet. Meanwhile, P3 has started to turn on, its gate being brought low by the rapidly dropping out. P3 turning on brings the sources of P2 low and turns P2 off. With P2 off, out crashes down. The snapping action is due to greater than unity loop gain through the stack caused by positive feedback to the source follower transistor. When the input is brought low again, an identical process occurs in the upper portion of the stack and the snapping action takes place when the lower threshold is reached. Out is fed into the inverter formed by P4 and N4.
Is defined when the first equation or when M2 starts to turn on. As M2 starts to turn on, the output starts to move toward ground, causing M3 to start turning off. This in turn causes Vx to fall further, turning M2 on even more. This continues until M3 is totally off and M2 and M1 are on. This positive feedback causes the switching point voltage to be very well defined. When the last equation is valid, the currents flowing in M1 and M3 are essentially the same. Equating these currents gives the first equation, which is V in is equal to VSPH equals to VTHN2 plus Vx. Since the sources of M2 and M3 are tied together, VTHNI equals VIMB. The increase in the threshold voltages from the body effect is the same for each MOSFET. The combination of the first and second equation yields to the beta 1 over 2 quantity VSPH minus VTHN quantity squared is equal to beta sub 3 over 2 quantity VDD minus Vx minus VTHN sub 3 quantity squared. The threshold voltage of M1 given by VTHN in this equation is the zero body bias. Since the sources of M2 and M3 are tied together, VTHN1 equals VIMB. The increase in the threshold voltages from the body effect is the same for each MOSFET. The combination of the first and second equation yields to the equation of beta sub 1 over beta sub 3 is equal to W1 L sub 3 over L sub 1 W sub 3 is equal to the quantity of VDD minus VSPH over VSPH minus VTHN quantity squared. The threshold voltage of M1 given by VTHN in this equation is the zero body bias threshold voltage equals to 0.8 volts in our long channel CMOS process and 0.25 in the short channel process. Given a specific upper switching point voltage, the ratio of the MOSFET transconductors is determined by solving this equation. A general design rule for selecting the size of M2, that is beta sub 2, is to require that beta sub 2 is 1 over beta sub 3 is equal to W sub 1 times L sub 3 all over W sub 3 L sub 1 is equal to the quantity 1 minus 0.55 all over 0.55 minus 0.25 quantity squared. This will give us an answer of 2.25. The ratio set for M1 and M3, L sub 1 is equal to L sub 3 is equal to 2 and W sub 1 is equal to 22.5 and W sub 3 is equal to 10. For the lower switching point voltage, beta sub 5 over beta sub 6 is equal to W sub 5